So I want to digress for a moment. Before we get into today's regularly scheduled class, I want to give some advice. And I'm not going to go into too much detail about my problem. The solutions will be posted soon. Some of the times when you look at the solutions, I think part of the problem you're going to be like, oh my gosh, I can't believe it was right there. But there were some things I noticed. A lot of people struggled with integration and differentiation and evaluation and squaring. Now, spoiler alert, these are all things that are very useful. From today till the end of the semester, we're going to be doing differentiation or integration, or maybe both sometimes, almost every day. So, if you're struggling, practice and get caught up. But that's not the main thing I'm worried about. I saw a pattern emerging with the theme of the idea of simplifying. Now, I was not the only person who observed this. Another instructor, as they graded their problem, noted that one of their students on the exam had a computation that said, well, I have this, and they drew a little arrow, and they said, need calculator. Now, I wasn't 100% certain about whether or not engineers needed calculators to do this, so I called an expert. My wife has been working as an engineer for over 20 years now, and I said, okay, you work for a big company. Does anybody in your company need a calculator to know what 2 times a half is? After she stopped laughing, she said, I feel really bad for these students. I really want them to succeed. So she has a lot of empathy. But the answer was no. Now, I'm not trying to pick on anybody by pointing this out. I'm just saying you should have some faith in yourself, in the ability to simplify things. Now, you can succeed. I completely believe in you. Developing number sense is important. But as bad as this might be, this is just one example. For my problem, I saw dozens of people choosing to say the following. I'm not going to simplify, and then keep going forward. So here's the thing. This is, I want to sort of say what we say to students, what you hear as students, and here's what we mean. So, what do we say? Well, we've given instructions. You don't have to simplify unless told so. That's more, I don't know if it's exactly what it says, but that's the spirit. You don't have to simplify unless instructed to. I don't know if you've seen this before. Okay, that's great. So what do the students hear? Well, I don't know. There's this movie that came out a long time ago. You'd have to talk to your grandparents, called Gone with the Wind. At one point in time, it was the biggest movie of all time. And at the very end of that movie, the main character, Scarlett, the last line of the film, as God is my witness, I shall never go hungry again. So what the students hear is they say, as God is my witness, I shall never simplify again. And that's the mindset. So that's bad. Okay, that's not what we meant for you to hear. So what do we want you to hear? this is what we want. What you need to do is you should say, I will simplify if it helps. That's what you need to know. Simplify if it helps. Now, when is a situation when it will help you? If it's part of the instructions, because they're going to grade you on whether or not you simplify, that's going to help you. But there's another time. If you're about to take the output of one computation and feed it into another computation, don't put in a long expression when there's an equivalent shorter expression that involves simplification. Should I make this a little bit more explicit about what happened?
Yes.
So that there's no second guessing? Okay. There was, at one point, the following computation. You had to take this derivative. A lot of people got this derivative right. Many people forgot it. What rule do we need? Product rule. Product because it's two functions multiplying together. Okay, so product rule. All right. I love the chain rule. Spoiler alert. We can take what we learned in next lecture and show that the product rule is actually a consequence of the chain rule. So everything's chain rule. So okay, so we take this derivative. Now product rule works by you take the derivative of the first. Okay, so the derivative of e to the t is e to the t times the second plus the first times the derivative of the second, which is that. Okay? Great. A lot of people got this. Huzzah! But then the next thing you have to do is square this. So what did people do? They're like, well, as God is my witness, I shall never simplify again. So they said, okay, I'm going to square the whole thing. And 95% of the time or more, they got that squaring wrong. But what could they have done? Well, if you distribute, this is e to the t times t minus e to the t plus e to the t. So, if you simplify before squaring, this is the computation you have to do. Which one do you think would be easier to carry out? The second one, right? This is simplify if it helps. So that's my mindset. And I understand you're nervous. I get that. But build up some confidence in your skills to simplify. You can carry out basic arithmetic. We believe in you. And always think ahead. What's going to help me? That's what you should do. All right, so that's my small rant. And I think you've done well. I don't want you to be stressing out about this exam. So we'll go into details by the end of this week. I don't know if it's the next lecture or the one after that, but within the next few lectures, we'll go into details and say, okay, let's calm down. No need to panic. So, all right. So now let's go to our lecture. Oh my goodness, that was quite the thought for today. Hopefully we have enough time left for our lecture. Our warm-up problem. Sketch the level curve f of xy equals 2 for, and we have this function f of xy is, it's a piecewise function, which you're allowed to do piecewise functions for multivariable functions, x squared plus y squared plus 2y over 2x, or 0 depending upon the value for x. Did anybody do this problem as we were waiting for class to start? Anyone? Okay, I guess we can just do it now. Do it together. Okay, so level curve. When you see level curve, what does that say? Well, it actually just says it right here. It says, I'm setting my output to a fixed value. So I'm fixing my output. And the question is, what inputs gave me that? It's kind of like you're trying to run the machine backwards. Like if you think of a function as you plug something in, you get an output out. Now it's like, well, here's my output. What did I plug in? So which values of x, y give me a value of 2? Well, 0 is not 2, so I can focus on this other part. So, all right, x squared plus y squared plus 2y over 2x. So this is the function equals 2. What can we do to figure out what this looks like?
Simplify?
Simplify. Yeah, I think it'll help. I like that mindset. Well, for me, I don't like fractions, so let's get rid of fractions. Cross multiply, if you will. So we get x squared plus y squared plus 2y equals 4x. Now it's probably feeling a little bit more familiar. I'll move the x's so they're next to each other. I'll keep the y's next to each other. So we have this expression. Okay. What do we do? What do we do? Complete the square. Okay, what do I need to add in this suspicious gap here so I get a nice square? 4. You take the middle term, divide by 2, and you square it. Okay, and this will become x minus 2 squared. What do I need to add over here? You need to add the 1. And if you do that, you'll get y plus 1 squared. But you have to add on the other side. You can't just arbitrarily add 4 and 1. You have to make sure you leave things balanced so the equation is still true. So what do we end up with? X minus 2 squared, y plus 1 squared equals 5. What does that look like? Well, what is that? What does that look like? Circle. Can you tell me anything about this circle? Where's the center? Over at positive 2 and negative 1, so there's the center. Do you know the radius? Square root of 5. Now, it's not totally obvious what square root of 5 is, but I will point out that 0, 0 satisfies this relationship. So it goes through the origin. Okay, so something like that. All right. Good. Is this the answer? And why not? It's a level curve. When you draw a level curve, it's a sketch of a curve. So is this the correct answer, and why is it not? Ah, yes. Oh. Remember, if x equals 0, the output wasn't 2. It was 0. So how do we modify this picture?
Add an open circle at the negative.
Yeah, add open circles where x equals 0. And now this is the correct answer. So it's a circle, except you have to punch out 2 holes. Yes? Why do we have to punch out both these holes? Well, it's anywhere where x equals 0. So, where does x equal 0? X equals 0 is also known as the y-axis. So any place where this curve hits the y-axis, the function is specifically along the y-axis, the function is 0. Why did we say that? Well, you might notice that if x equals 0, this is not a very friendly expression. All right. So that was a reminder from a week ago. Oh my gosh. Whew. Okay. So, our second thought for the day, after simplify, if it helps, from Mr. Fred Rogers, or Mr. Rogers, as most people know him. There is no normal life that is free of pain. It's the very wrestling with our problems that can be the impetus for our growth. It's okay that you're struggling. Learning to deal with that and learning to overcome it, that's going to help you grow. And you can. I believe in you. Don't give up on yourselves. I'm not ready to give up on you. So what are we talking about today? We're finally going to do more calculus, right? This is calculus. We got to do more of that. And we're going to start getting to the idea of derivatives of multivariable functions. And we're going to do this by saying, well, it's hard. But we can do what are called partial derivatives. And those are pretty easy, intuitively speaking. They just say, well, don't think of it as lots of things changing simultaneously. Just think of one thing changing. And so we're going to take the derivative with respect to one of the variables. And we'll treat the other variables like constants. We'll get into some notation. There's the notation we've been used to for like dy dx. We're going to switch to this symbol here that looks like a d that's been slightly warped. We'll talk about that, and we'll talk about higher order derivatives. Because if you can take one derivative, why not more? So that's our goal. So let's talk derivatives. Now, from Calc 1, we learned, hey, I know how to find the derivative. So the derivative is measuring a rate of change. So I want to say, how does my output change with my input? So that's what you have up here, this f of x minus f of a. This is change in output. X minus a is your change in input. And then you just say, oh, well, just, when you get small, it looks very flat, and so it looks like a line. So it's like a slope of a line. So, okay, so let's think about it. We'd like to do derivatives for multivariable functions. We say, well, let's think about one thing we could try. We could put change of output upstairs. That just says, look at how the function differs from a nearby point. Then change in input. Well, change in input gets interesting because we're looking at how do we look at the change between 2 points. And that, we said, that's a vector. Now, will guess number 1 work? And why not? All right, will this work? No. In fact, not only does this work, hashtag epic fail. It's just absolutely gets crushed. Not a chance. But what's wrong here? What are you trying to do? Divide by a vector. We can't do that. You can't divide by vectors. So it's not going to work. So you say, okay, well, that's my problem. So I'm trying to divide by a vector. So I'll do the same thing, but except instead of downstairs being a vector, I'll just change it to the length of the vector. So again, it's sort of like changing output, change in input, but somehow an absolute value. Will this work? And why not? Well, okay, I'll be honest with you. This will not work. Hashtag subtle fail. The reason it fails, because it feels like you're almost there, is you lose information. When you take the magnitude, you lose directional information. And that's actually important when you went back and did derivatives. So there are things that aren't going to work. So you're like, okay, so what can we do? So an idea comes to us. It says, let's work in cross sections. So our basic idea, we have a surface. So here's our surface. Now what we can do is we can slice. So there's two kinds of slices we'll look at. We'll fix either the x variable, which is this orange part, and if we fix just the x variable, now instead of having a function of two variables, a surface, in the slice, we get a curve. Now, why do we like that? Well, because we know how to talk things such as tangent lines. We can work on curves. So by slicing, we can say, now instead of up here we have this function, z equals f of x comma y, I can reduce it down to just a function of a single variable, and I can pull out all the wonderful single variable calculus tools we know. But I can also do a different kind of slice. So I can slice over here where I'm fixing not a value of x, but I'm fixing a value of y. And when I look at this slice, I'll get a different picture. But now I say, I have a curve which is a function of x. Because x is the only thing in that slice which varies. Because I fixed the y value by being in the slice. So again, we can come in and say, I can talk about what's happening at any given point. I can talk about derivatives here. So that's our great aha. We can say, instead of trying to actually think of derivatives of multiple things changing simultaneously, we're going to work in the slices. And what does that give us? It says, hey, we get to use our old tools. So, as we've said before, multivariable calculus is really single variable calculus. We're just going to do it multiple times. So in this case, when we're taking derivatives, if I have a function of multiple variables, I'm just going to take derivatives in each slot. So what happens? Well, the thing to remember is when you're taking a derivative, know what is it you're taking derivative with respect to, which variable is the one that can change, and then you treat all the others as constants because you're in that slice. So we have to have notation to make sure we know which derivative we're talking about. So what's our notation? So we're going to read this as partial f, partial x. And this should be thought of, it's the derivative of f with respect to x. But we use the word partial to indicate it's a function of multiple variables. And the way we interpret this, this says how f changes as we change x. Partial f, partial y, how f changes as we change y. So you're taking the derivative, whatever you see downstairs, that's what you clue off of. If I see an x downstairs, take the derivative with respect to x. If I see a y downstairs, take the derivative with respect to y. All right. Some words about notation. Our old notation, we used the D symbol. And we'll still use it from time to time. When you see a D, that means that there's a function with one variable. So like dy dx, when y is a function of x. That's what we used it for. Now we're going to switch to the partial symbol. Whenever you see this symbol, that says, oh, it's the same thing as d. It just means the same thing. Now, taking a derivative, it just says, oh, this function has multiple inputs. All right, now, some handwriting practice. How do you write this symbol? So, you start in the upper left. So you start and you go around.
It's a backward 6.
Kind of like a backward 6. Yeah, that's not bad. So practice. You don't have to make a noise, but practice that symbol. You will write it often. Okay, a few notes about notation. So for our d notation, we're familiar with this from Calc 1. d dx means take the derivative with respect to x of whatever you're working with, so in this case, f of x. And we write this as f prime of x. Occasionally, you will see another notation. If you go on to differential equations, you'll see that there's a whole lecture where we go through and use the notation capital D, which stands for the derivative operator. So for us, well, we're just going to switch from d's to partials. Partial x says take derivative with respect to x of f of xy. Now we have to be careful. We can't just say f prime, because we have to say, well, wait, which derivative did you take? So instead of having a prime upstairs, we put a little subscript. So f sub x says take derivative with respect to x of x comma y. F sub y says take derivative with respect to y of f. So partial y of f of xy. Similar for the d's, you can have a subscript saying d sub x means taking the derivative with respect to x of the function. D sub y means you're taking the derivative with respect to f of the function. All right, so the punchline for today. We can take derivatives. We just do it one variable at a time, and we have some new notation. Any questions before we move to some examples for a few minutes? All right. So, an example. Find all partial derivatives of the following function. So I have h of x, y, z, 3x squared y plus log of x squared plus z plus sine of y arctangent z. Okay, so before we start, it says find all. How many will there be? And how do we know? 3. How do we know there will be 3 partial derivatives? There's 3 variables. Okay, and particularly, you don't need to count what's over here. You need to count how many inputs you have into your function. Okay, so we get to do this 3 times. All right, so one partial derivative is the derivative with respect to x. So we can say, okay, we'll probably usually say something like partial h, partial x. So as we go through here, taking the derivative with respect to x, what do we think about y's and z's? They're constants. That's what we're thinking about it, right? So, we think here x equals variable, y, z equal constant. All right, that's our thought bubble. So, with that in mind, what's the derivative of 3x squared y with respect to x? 6xy. The y just comes along because it's a constant. What's the derivative of log of x squared plus z with respect to x? Yeah, so whenever you have a log, write a fraction. The inside part goes downstairs. The upside part is the derivative. Derivative of x squared plus z with respect to x? 2x. You'll notice here we don't just say the derivative. We have to add that information with respect to what? Because it matters. This last part, sine of y arctangent z. What's the derivative of that with respect to x? 0. Sure, there's a lot of stuff there, but none of it has x's. So we're done with that derivative. All right. Well, let's move to the next one. Partial h, partial y. Okay, so now y is the part that can vary. Treat x and z like constants. The derivative of 3x squared y with respect to y. What is that? 3x squared. Essentially, we're thinking of it like, oh, it's something that's constant times y. How about the next term, log of x squared plus z? Derivative of that with respect to y? 0. There's no y. The last part, derivative of sine y arctangent z. What will that be?
Cosine y arctan z.
Right. So the derivative of sine, that's cosine. We don't need to do a product rule because there's not two functions of y. There's one function of y and something that's not a function of y, which we're treating like a constant. All right. Our last piece. Okay, so what do we have? We have partial h, partial z. So, for the first term, the derivative of 3x squared y with respect to z, it's a constant, so the derivative is 0. Log of x squared plus z, derivative of that with respect to z.
1 over x squared plus z.
Yeah, so right, whatever's inside in the denominator, the derivative of x squared plus z with respect to z upstairs. That's a 1. Derivative of sine y times arctangent of z with respect to z. Yeah, so sine y is a constant. And I'm so excited because I heard people saying the derivative of arctangent with no pausing. 1 over 1 plus z squared. And there you go. There you go. All right. Any questions on that one? Looking at time, I think I might skip the next one. I'll see if we have time at the end to come back. Okay. Well, that's first order derivatives, but we can also do higher order derivatives. So we get to not do just 1 or 2. We can do as many as we want. So we can keep taking derivatives. But now things get more interesting. Before, in Calculus 1, we had just one first derivative. Now we've already seen we've just had a function that had 3 first derivatives. So now we're going to get to second derivatives. The possibilities grow even bigger. So if I have a function with 2 inputs, x and y, there are up to 4 second order derivatives. So I can take the derivative with respect to x twice. And one way to denote that is partial squared f partial x squared. And that's f xx. I could take the derivative with respect to y twice. So the derivative with respect to y of the derivative with respect to y of the function fyy. I can also look at mixed derivatives. Partial squared f partial x partial y, which says what? Take the derivative with respect to x of the derivative with respect to y, which is fyx. Now, I will say there's this small subtlety that when you look at how things are going, they actually go sort of opposite of each other. So if you look at the ordering downstairs, for the notation on the left with the partial symbols, it goes in the opposite order from the notation on the right with the subscript symbols. Don't stress too much about that. It's a technicality with conventions. But this says, take the derivative with respect to x of the derivative with respect to y versus take the derivative with respect to y of the derivative with respect to x. And there's a natural question that people may ask. Well, do I really have to do both of these things? And the answer is, technically speaking, they don't have to be the same. There are examples, but if f is nice, and spoiler alert, we work with nice functions. Essentially, if you can write something down, it's nice. You really have to get to some weird stuff involving division by 0. Then, I don't know why I started this with but. These will be the same. So for this semester, you can assume these are the same. And for any function which you would probably meet out in the wild, just randomly roaming around, they'll be the same. You have to be a little bit exotic to make it break. So that's some good news. You don't have to stop at second derivatives. I will say that we will get up through second derivatives. We're going to see some important applications when it comes to optimization. But you can go as high as you want. Here's an example of the fifth derivative of a function, partial x, partial z, partial y, partial z squared of x, y, z. Now you might think that's a curious combination. It seems to form this zzYzx. Zizix. Is anybody familiar with Zizix? Have you ever seen it somewhere? If you drive from Southern California to Las Vegas, one of the very last exits before you hit the California to Nevada border, so just before the casinos, a few miles before the casinos, there's an exit called Zizix. So it is a real place in California. Spoiler alert, don't try this in Wordle. They won't accept it. They have made a movie. In fact, they've made two movies about this. One of them is called Zizix. One of them is called Zizix Road. I think it was Zizix Road that had a box office of $20. So they made a movie, and it made $20, which set a record at the time. So it was not you haven't seen it, I'm sure. So, okay. So we can take higher order derivatives. So let's try this out. Find all the second order derivatives for the following function. Now, second order means you have to take two derivatives. So if you want to get to second order derivatives, what do you need to do first? Got to get to first order. Okay, good times. So I'm going to use the subscripts here, f sub x. Take the derivative with respect to x. Uh-oh. What rule do you need here? Product rule. All right. Derivative of the first, 3x squared, times the second. I'm already regretting my choices by making this problem. Plus the first times the derivative of the second. Well, the first is x cubed. And then the derivative of cosine is negative sign. So I'm going to change this plus to a minus. And then I'm going to get a y coming out. Why does the y show up? Yeah, I'm treating it like a constant, and I'm doing the chain rule. Then I still have the second term. The y is the constant. Derivative of e to the minus 2x. A minus 2 comes down. This will become plus 2y e to the minus 2x. All right, there's the f sub x. So many things to learn. Okay, now we go into f sub y. Do we need to do the product rule this time?
No.
No. So what will we get?
X cubed sine xy.
Okay. There's definitely a minus. And there is definitely a sign of xy. What goes in front? X to the fourth. How did it go from x cubed to x to the fourth? By the chain rule, when you're taking the derivative with respect to y, another x will come out, and we'll have it join with that x cubed. How about the derivative of minus y e to the minus 2x? What will that become? So we're taking the derivative with respect to y. Derivative of minus y e to the minus 2x with respect to y. Yeah, it's minus e to the minus 2x. That will go away. All right, so that's our first order out of the way. So for second order, we begin. Which one do you want to do first?
Bottom.
And why? Yeah, FYY looks a lot easier. Okay, yeah, we can do this in any order. We have to do them all. So might as well be nice to ourselves. After all, we like ourselves. fyy. All right, the derivative of minus x to the fourth sine of xy. We're taking the derivative of that with respect to y. What do we get? Minus x to the fifth cosine xy. Derivative of minus e to the minus 2x with respect to y? 0. Okay, woohoo, 1 down. And 3, but we can just do 2 to go. And we have enough time to do the last 2. Plenty of time. All right, so what's left? Well, we have our fxx. And then our other one that we have to talk about, and yes, we do have to talk about it. We need to talk about fxy, which is the same as fyx. So, maybe let's come down here. We have these derivatives. This is a nice function. Essentially nice, you should see, if you can take derivatives and keep going and take more derivatives, it's nice. So this is nice. We have 2 choices. We can either take the derivative of the first partial derivative, so f sub x, we can take the derivative of this with respect to y, which involves 3 terms, and simplify. Or we can take the partial derivative with respect to y and take the derivative of that with respect to x. Now the question is, which one should we do? The answer is that in some sense it doesn't matter. Occasionally one is a little bit easier to work with than the other. It feels like the second one has fewer pieces, so I feel like that one might be easier to work with. Here we'd have to do a product rule. Sorry, we wouldn't have to do a product rule, but we'd have to do a product rule here, but we don't have to do product rules there and there. But here there's one product rule and something simple. So it's a slightly easier computation. So when you're doing that mixed partial derivative, you can think about, well, which one is a little bit easier if there is one that's easier. Okay, so it sounds like we're going to take the derivative of the second one with respect to x. So just to help make it abundantly clear which computation I'm doing, I'm going to put it here. Taking the derivative with respect to x of the derivative that we already found with respect to y. So for the first piece, we have to do a product rule. We have x's showing up in 2 places. What's the derivative of minus x to the fourth? Minus 4x cubed. Leave the second term alone for the time being. Now, we're going to take the derivative of the second term with respect to x. So we have that minus x to the fourth. What's the derivative of sine of xy with respect to x? Y cosine xy. This y came from where? Chain rule, as someone said. Beautiful rule. Beautiful rule. We're going to talk about that rule next time. By the way, next time, action-packed lecture. What took us like a week and a half in Calc 1, we're doing in 1 lecture. Good stuff. Good stuff. Okay. I'm not done yet. That's sort of the first part. Derivative of minus e to the minus 2x with respect to x. 2e to the minus 2x. And if you want, you can go through and take the derivative of this first derivative with respect to x, take that derivative with respect to y. You might have to do some cleaning up. They are equal. But in the interest of time, we still need to do our fxx. So, especially in the interest of time, we'll just go through it. Derivative of the first, 6x times the second, cosine xy, plus 3x squared times derivative of cosine xy. We're taking derivative with respect to x, which makes derivative of cosine is negative sine of xy. Chain rule, because we're taking derivative with respect to x, a y comes out. That's the derivative of the first part. Then come here, minus, well, the derivative of the first, 3x squared. And then everything else we're treating as a constant. Right? Derivative of the first times the second. Then the first times the derivative of the second. Derivative of sine of xy with respect to x. Cosine of xy times y. Since we already have one, that makes it a y squared. Then we come to our last one, derivative of 2y e to the minus 2x with respect to x. Minus 4y e to the minus 2x. Now, I have a minute left. We don't have time to do this problem, but I do want to ask you one question. Here I have a function, g of s, t, and u. And it says, find the partial derivatives of the following function. My question to you, if we go from xyz to stu, do we have to learn a whole new calculus theory that can handle this? No. It's the same process, just a different symbol. So use the same tools that you know and love. All right, that's it for today. Come back next time for our action-packed lecture. Have a great day.